Today we're going to be learning about Bernoulli's equation. Bernoulli's equation is pretty much derived from the mechanical energy equation. You should be familiar with this as energy conservation principles were covered during your 2210 class. But in essence, let's assume we have the following situation. We have a pipe coming in with a specified diameter of dn. The water is flowing at a velocity Vn into this pipe. The pressure at the pipe at that inlet point is Pn, and it is a height of Hn from our reference coordinate frame, here indicated here. On the other side, we have a different diameter out. We have a different velocity out, a different pressure out, and a different height difference than from when we came in. So how we're going to set this up is pretty much our accounting equation. It's going to be accumulation is equal to in minus out plus generation minus consumption. You've seen this equation pretty much all the time in 2210. And what we're going to derive for you today is how we get Bernoulli's equation from that. We're going to assume that for unsteady conditions you will have accumulation of energy. And that energy is going to cross the system boundaries that we've indicated for you here. Energy can be generated, it can be consumed and converted to another form of energy, right? So we can have pumps, we can have work being done, we can have turbines and all those sorts of things that are converting energy, fluid mechanics energy into potential electrical energy or going the other way. So the main energies we're going to look at is kinetic energy, potential energy, flow work, compressibility of fluid, friction, and some shaft work. So first let's take a look at kinetic energy. Kinetic energy is pretty much the fluid is in motion and it is due to the velocity. And kinetic energy is equal to 1/2 mass times velocity squared. Now the change in kinetic energy is going to be the difference between the velocity in squared minus the velocity out squared. Now very important to note here, it is you square each individual velocity. A lot of times students make the mistake by saying Vn minus V out, calculate that and then square it. That is wrong. That'll get you the wrong answer. You got to take the Vn squared minus V out squared, and then you can have them and multiply by mass. This fancy notation here, the specific kinetic energy, all we've said is this is per unit mass, and so we've divided through by mass. Next, let's take a look at potential energy. So potential energy is the fluid is due to a positional change in the gravitational field. So if you go from a lower, such as we have at Hn, to a higher, as we have an H out, there's clearly a potential energy change that exists. Now we calculate potential energy as mass times gravity times height, and the change in potential energy is mass times gravity times the change in height. And once again, specific potential energy is just the potential energy per unit mass. Next, we have flow work. Flow work is due to the amount of work due to the pressure that is in the area, and so we calculate work as force times length, but we know how to calculate force, right? That is pressure is equal to force over area, so we can rewrite force as pressure times area. And since we have a length here, we just multiply the area times the length to get volume. And so workflow is equal to pressure times volume. And then if we change the pressure, you will have a change in the workflow. So Pn minus P out is going to give you a change in work here. And we divide through by density because density contains volume. And so volume and volume cancels out, and so you have force. All right, next we have compressible. For the most part in this class, we're going to deal with incompressible fluids, but if you have a compressible situation, you need to account for the reversible conversion between the internal energy and the mechanical energy that exists, and so you have this integral of the pressure as it's changing with respect to volume in this case. But if you have an incompressible fluid, which we deal with for a lot of problems, that term will just go to 0. Next, shaft work. So if I have a pump in my system, or if I have a turbine in my system, I have to account for it in terms of shaft work. And then friction losses. We have major and minor friction losses. We'll definitely talk about work and pumps and major and minor losses later in the semester, but for right now, you just need to realize that it's there. It actually reduces the flow, so what you need to do, it will always be negative. And so we end up with this situation. Accumulation is equal to in minus out plus generation and consumption. We've made the following assumptions. We assume that we're in a steady state condition. If we're in a steady state condition, that means accumulation has to go to 0. We have one inlet and one outlet. We are interconversion is only between mechanical and thermal energy. We don't have any chemical reactions, so generation and consumption goes to 0. And so we're dealing with conservation of mass and conservation of linear momentum, and so we end up with this equation down here that is pretty much saying this is your potential energy change, this is your kinetic energy change, this is your work due to pressure energy change, this is your change in shaft work, this is your change in friction, and this is your compressibility change. Note all of them have the m dot out there, and so we can adjust that as such. First we're going to say steady state, that goes to 0. We're going to say we have an incompressible fluid, so we can get rid of that task. Then we divide through by m dot, we end up with these terms, and then we end up with what is known as the extended Bernoulli equation down here. But we can simplify that even further. If there is no shaft work being done, and if we're dealing with no friction, then those last two terms cancel out, and we end up with the simplified Bernoulli equation. Please note that when we have the statement of inviscid flow, really what we're saying is that we have no friction, or we're assuming an idealized condition, and so we can neglect friction, and so we can cancel those terms. So, in summary, my simplified Bernoulli equation, I have my potential energy change, I have my kinetic energy change, and I have my work due to pressure change. Now let's take a look at that in practice. We have one more situation here and how velocity relates to each other and into this. So for confined flows, meaning I have some sort of syringe here, it contains a liquid, let's just say saline, and I'm pressing the plunger in here. It has a velocity of v1 here, but it has a different velocity of v2 there. Why? Because the diameter changes. And we got to assume that conservation of mass is valid. So that means that the amount of mass in to my system has to be equal to the amount of mass out, steady state, and we're assuming one inlet and one outlet. Now our mass flow rate is defined as density multiplied by volumetric flow rate, which is Q in this case. We can further specify that Q, or volumetric flow rate, is equal to velocity times area. And so you end up with the units of meter cubed per second for volumetric flow rate. You will use volumetric flow rate for the rest of the semester, I promise you. Then we have, we can write the following equation. Mass flow rate is equal to density multiplied by velocity multiplied by area. And if mass is conserved, we have to say the mass flow rate in has to equal mass flow rate out. And so P1, V1, A1 has to equal P2, V2, A2, where 1 is in and 2 is out. Now, we can further simplify this down if we assume that we have an incompressible fluid. If we have an incompressible fluid, then guess what? The density 1 is going to be equal to density 2. And if that's the case, then we can simplify this further down to saying that Q in is equal to Q out. Please note that this can only be stated if you're dealing with an incompressible fluid. If you do not have an incompressible fluid, you cannot simplify down to this equation. You have to work from this equation. Now let's take a look at an example.
here's the graph, and here's the description. The description reads, a stream of refreshing beverage of diameter d equals 0.01 meters. Let's see what that little d is. That's down here, okay. Flows steadily from a cooler with a diameter of big D, 0.2 meters, as shown in the figure. Determine the volumetric flow rate Q from the bottle, so this Q, into the cooler if the depth of the beverage in the cooler is to remain constant at an H of 0.2 meters. So let's talk about Jim. What is physically happening in this problem? Well, I have a cooler, there's liquid in it, and I'm pouring something into the top and I'm draining it at the same time from the bottom. I know that at the bottom my diameter is 0.01 meters, and so it probably has a specific volumetric flow rate, and I have the Q at the top. So I'm probably going to say something about maybe Q in is equal to Q out in this system, right? And so we got to use our knowledge to date to do this. So I'm going to assume steady state because this question doesn't specify otherwise, and so steady state is a reasonable assumption. I'm going to say inviscid, meaning I can neglect friction losses, and that it's incompressible. All I know is it's a liquid. It's probably, assume it's water. And then we're going to assume that there's no shaft work because there's no pumps, no turbines, nothing like that added, and no friction losses, which is kind of repetitive from inviscid. Here are my list of knowns, and here's what I need to find. I need to find the volumetric flow rate, Q, at the top of my cooler. I'm going to use this equation, which is a Bernoulli's equation, and so I would identify this primarily as a Bernoulli type problem. Now, the key to the Bernoulli problems is in picking your points on your diagrams. And so you got to be very careful which points you pick, because if you pick the wrong ones, you won't be able to solve it. If you pick the correct ones, you will. So whenever we see a place that's open to the atmosphere, we almost instantly want to pick that point because that means the pressure goes to zero at that point if we're dealing with gauge pressure. And so here I've picked the pressure point up here, P1, and I've picked the point P2 to evaluate because both of those are open to the atmosphere. So P1 and P2 is going to be equal to 0. I also happen to know that there's an H, a height difference between them. So if I set my coordinate frame to be here, Y, pointing up, I know that that H, or Z1, is going to be H, and Z2 is going to be 0, because my coordinate frame is here for Z. Plugging all of that back into Bernoulli's, I find this expression. Now you're going to say, well, Dr. Harley, that equation doesn't look the same as the one that I have on this graph down here. I know, but this form is much easier to learn if you're just starting out using Bernoulli's. And believe me, it'll result in you making far less mistakes. So this is the form that I suggest students always start when they're starting to learn how to do Bernoulli's. We can also say that from conservation of mass principles, okay, mass flow in has to equal mass flow out, but we're dealing with an incompressible fluid. That means I can say that Q in has to equal Q out. So the Q at point 1 has to equal Q at point 2. That means the velocity at 1 times area at 1 has to equal velocity at 2 times area times 2. And I can find area because I've been given the diameters, and I can write the velocity at 1 with respect to velocity at 2. And so you see, I have two equations and I have two unknowns. My unknowns at this stage is my velocities, and so that's what I want to solve. When I combine those two equations, I then find an expression for V2 that looks that ugly equation. I plug in all my values that I've been given, and I find that V2 is 1.9 meters per second. And then since I already have V2, I can just go ahead and calculate Q, and that is just going to be then my velocity value here for V2 multiplied by my area value, and bam, I have Q. Remember for Q, you don't, although I'm asking you for the Q here, you have to remember that if mass is conserved, and if you have an incompressible fluid, that the Q here is going to be equal to the Q there. Now let's take a look at a second example. This example here is called a Venturi meter. You have this slanted pipe, water is flowing up and down this pipe, and I've attached a manometer to my pipe. Now, what is very important from Venturi meters is you can only apply fluid statics equations to the fluid statics part of the problem, the manometer, this part. Fluid is not flowing in my manometer, it's stationary, so I can use my static equations. Fluid, however, is flowing through this pipe, and so I have to use Bernoulli's to get from point 1 to point 2. So the question says, water flows through a pipe reducer as is shown in the figure. The static pressure at point 1 and point 2 is measured by the inverted U-tube manometer containing oil of a specific gravity Sg less than 1. And they want you to determine the manometer H reading. Now obviously this question doesn't have any numerical values, and so I'm asking you to derive the variable equation that you would use to find H. So this is a complex problem because you've got to combine your Bernoulli's knowledge, your conservation of mass knowledge, along with your manometer knowledge. So, steady state. I've already identified that this is a steady state problem. We're dealing with inviscid and incompressible. There's no shaft work, no friction, there's no pumps, nothing like that, and I'm conserving mass. In essence, when I'm summarizing, Jim, this would lead me to believe that I'm dealing with a Bernoulli's problem, a manometer problem, and a conservation of mass problem. Those three things you would probably mention in your Jim. Now, known, you can see here I've just said C diagram. That would be allowed, but only in the instances in which you actually add the information to your diagram, or if it's all variables. You need to find H, and here are my equations. See, here's Bernoulli's, here's conservation of mass, and combine those two equations and you come up with this expression down here. And then also, here's the third equation, your manometer equation. So let's take a look at, one second, let's take a look at my manometer equation. I'm going to start here at P1. Okay, and I'm going to go up. So if I go up, am I going to go positive or negative? Yes, you're right. We're going to go negative because we're going up. So I'm going up, that specific weight of water multiplied by that height change. Then I'm going to go from this point up to this point. So that's negative again, specific weight of water times this length. And then I'm going to go from this point to that point at specific weight of water times H. From here to here, right, that's a horizontal change, so no contribution. And then from here to here, I got to go down. So that's going to be plus specific weight of this oil multiplied by H. Or you can just say that's going to be your specific weight of water times your specific gravity times H. And then you're going to go from this point over here to this point here, which is point 2, which is an L. It is also moving down, so we're going plus. So that specific weight times that length, and that then gets you to this point P2. Now note, I was able to write my equation for Bernoulli's as P1 minus P2. I had arranged it particularly that way. And I do the same for my manometer. And because it's P1 minus P2, it's identical between the two, I can set both those sides equal to each other, which is what I do in this case. And then you see I have H in here, and all I have to do is just rearrange that expression, and I find my expression for H.